Hey everybody, it's Mrs. Harbin. We're video notes 10-1. Let's get busy. Alright, we're talking about reactions as usual. Here's our objectives. Little bonus for you. Read section 18.1. To examine a couple figures and answer questions A, B, and C for each of those. Put them in your notes. Alright, show me them when you're doing your open note quiz. Alright, so here's some of the things we'll be exploring in this unit. Okay, how fast will a reaction occur? Will it even happen? And what makes it happen? Okay, so what kind of reaction is this? Hopefully you see two reactants, one product, and you're thinking combination or synthesis. Alright, so let's talk about what has to happen here. Iron is being held together by metallic bonds. Oxygen is being held together by covalent bonds. You have to break these bonds, break those bonds, and make these bonds to make this happen. So we're going to talk about what's going on. Alright, so how fast will that happen? Well, that's the rate. You know, the rate is how fast will this form, or how fast will these go away? And when we say how fast, we mean how much of this goes away in a certain amount of time we can measure, or how much of this forms in a certain amount of time we can measure. That's going to be the rate. Okay, so the rate of a chemical reaction is the change in the concentration over time. Okay, change in concentration. Remember those these brackets mean concentration over the change in time. Okay, what can we measure concentration in? Molarity. What can we measure time in? Seconds or minutes. So these are some possible units. These are some possible units for rate. But what we have to measure is the amount of reactants going away over time, or the amount of products forming over time. How does rate compare to time? Okay, so for you to get to class, it's your change in where you are over how long it takes you, your change in time. Okay, so if you run to class, your rate is going to increase. So you'll get further in a shorter amount of time. Okay, the rate has to be compared over time. So if the rate is quick, so if it's a high rate of reaction, then it's taking a short amount of time. So they're inverse to each other. They're opposite. So a high rate means a short time. Okay, a low rate means a fast time. Wait, a long amount of time. What did I just say? Okay, so the lower the rate, the longer it takes. The faster the rate, the shorter it takes. They're inverse of each other. They are not each other. Okay, so how can we measure that? So here's the time going on for this reaction. Here's the molarity, or the concentration of this ion forming over time. Okay, here's a graph of it. So how do we figure out the rate? Well, we take the change in the concentration, so you subtract them, over the change in time for that period. So we got to subtract those, put them over each other. Hey, it's negative. Why? Because notice the amount of the S2O8, -2 ion, is decreasing. So we say that it's a negative rate. That just means that the substance is going away. Okay, the reactants go away over time, the products form over time. So it depends which one you're looking at to talk about the rate. Okay, so why do these reactions happen anyway? Well, we have this theory in chemistry called the collision theory. And it is just like it says, collision theory. Collision theory. Things have to collide in order to react. So step one, collision. Now, every collision doesn't lead to a reaction. So the collision has to have enough energy, okay? And the enough energy is called activation energy. So that's the amount of energy it needs to go. All right, and the right orientation means that the molecules or the atoms have to collide at the right angle or hit each other in the right spot to cause a reaction. So step one, molecules or atoms collide. Step two, they have to have the right amount of energy when they collide. And step three, they have to collide at the right angle or the right spot. Okay, so think about the activity we did in class when we talked about the home run hitting. Okay, all reactions have to have these three things in order to happen. Okay, so what influences those collisions? Well, the mechanism, the way the reaction happens. All right, what happens first in the reaction? How much energy does it take to make it happen? There could be steps. Okay, so there's steps in a reaction. Is the reaction mechanism. Reaction mechanism is the steps. Okay. The nature of the reactants. Are the molecules complicated? Are the molecules simple? Are they simple? Complicated? Do they have really strong bonds? Do they have weak bonds? So that's nature of reactant is one thing to look at. The mechanism or the steps the reaction has to go through is another thing to look at. So those are two things that influence the collisions. All right. So what about the orientation of the molecules? Okay, so these two molecules need to collide. If they collide at this angle, then the bromines break off and make a new bond, and the NOs break off and make a new bond. So what is this reaction? This is two BRNO molecules react to form a Br2 molecule and two NO molecules. All right? So two of these have to collide at that right angle to make the Br2 and the two NOs. Okay? If they collide at this angle, successful collision because it's, right orientation. This is the correct orientation, this is 2. But what if they collide at the O side? No reaction occurs. Okay? So that's what it means by the proper orientation of the molecules. Okay? The steps. Let's bake a cake. If you bake a cake, you got to get ingredients. You got to mix. You got to pour in pan. You got to bake. Okay? Now, I know there's a lot more than that, but okay, so here's some steps to get this reaction going. The rate determining step is the one out of all of these that takes the longest. You cannot go faster than your slowest step. So what is this one? What's the slowest step? Hey, phone's ringing in my house. All right, the slowest step is baking it because it might take 40 minutes to bake it. And this might only take 5 minutes. This might only take 10 minutes. This might take 10 minutes. Okay, so the 40 minutes of the baking is the slowest step. So that's the rate determining step. Okay, there goes my answering machine. All right, so the rate determining step is the slowest step out of all of them. Okay, the rate determining of cake making is baking, probably. Okay, we'll think of some more of these. But so how fast is the reaction going to go? It can't go faster than the slowest step. So that's the rate determining step, the one that tells you how fast it's going to go. All right, nature of reactants. So this is pretty complex. All right, this is complex, but these pieces are little. So the complexity of the molecules can make a reaction go slower or faster. Super complex molecules will probably take a little bit longer to react than not as complex molecules. All right, so what if we had a bunch of pens and a bunch of pen caps and we put them in a box and we shook them up? Well, they're going to collide, but how many, when they collide, get the cap on the pen? Okay, so it's got to be at the right angle, it's got to be with the right energy to get the cap on the pen. That's kind of what a chemical reaction's going through, all right? Touche. So those are things we can't control. So let's look back. We can't control which step takes the longest. We can't control that. Well, we might be able to a little bit, but that's the one that determines the rate. So that's called the mechanism. We really can't control how complex our reactants are. Okay, but what can we control? We can control the temperature of a reaction. So the higher the temperature, usually the higher the rate. All right. Why? More collisions? So this is what we notice, but can we explain it? Well, if you had a higher temperature, you have more collisions with more energy, so more of them are going to react. Okay. Higher concentration. Remember, this means concentration means molarity. All right. So higher concentration is going to be a higher rate. Why? Because more molecules means more collisions. More collisions means more chances of reacting. Now remember, all of this is opposite too. Lower temperature means lower rate. Lower concentration means lower rate. So these are opposite effects. You can slow a reaction down by cooling it. You can speed a reaction up by giving it higher concentration. Surface area. Higher surface area, higher rate. Why? Because there's more places to collide. More collisions means higher rate because more of them could be successful. Lower surface area, lower rate. Okay, and then a catalyst or an inhibitor. A catalyst speeds up a reaction, and I'll tell you why in a little bit, because it's then the reaction is a different kind of collision that causes it. Okay, so you can change the kind of collision that it takes. An inhibitor slows down a catalyst. Okay, so we can control the rate of a reaction with these 4 things, and these 4 things can help control or change the rate. Hey, which one is this showing a picture of? All right, this is one of the 4 factors on this page. See if you can decide. Okay. This is saying faster rate. This is saying slower rate. This is the carbon dioxide coming off. Which one has a faster rate and why? Right. Dun, 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 dun. Hopefully you're thinking, tell me in class. Okay. So, another thing that helps us understand chemical reactions is heat. Delta H is enthalpy is heat. Okay. Heat. Delta H is enthalpy is heat. We talked about it. We talked about heat is on the left side of the arrow in a chemical reaction. Okay. Left, right. If heat is on the left side, it's endothermic. All right. If heat is on the right side, it's exothermic. If it feels cold, then heat's being absorbed, so it's endothermic. Okay. If water's boiling, we got to take this water and turn it into this gas. All right. So it has to absorb energy, so that's endothermic. So all of these are delta H's. Endothermic is positive delta H. Exothermic is negative delta H. All right, so this is positive delta H. So we're going to be talking about heat a little more because it's one of the things that helps us decide if reactions are going to go. Oh, energy diagrams, yay! What do you have to be able to recognize in an energy diagram? Reactants, products, activated complex, activation energy, delta H, and decide whether it's endo or exothermic. Okay, what's an energy diagram? It's a graph. The graph is going to have energy on this axis. You should probably sketch this. And this is going to have the reaction on this axis. All right, you should be able to label those axes. Okay, energy increasing here. A lot of times we do kilojoules or calories or something. Okay, on an energy diagram, we're going to have reactants and we're going to have products. All right, the difference between the reactants and products is the delta H. The difference between reactants and products. This has to be a negative delta H, so that's exothermic. The energy from the reactants to the top of the hill is called activation energy. Okay, and so E for energy, A of activation. So that's the energy it takes when they collide. You have to have this much energy. Okay, delta H is on there. This is exothermic. So then this is the only thing we haven't talked about yet. That's what we have at the top of the hill is the activated complex. So you're going to have to be able to draw these energy diagrams and tell what each of these things are in terms of energy. Okay. All right. So, hey, look, there's an energy diagram. Reactants, products. The difference between the reactants and products is the delta H. This delta H equals positive because it increases. Here's your energy. It takes more energy to be products. Activation energy is the energy to get up the hill. Okay. From the reactants to the top of the hill is the activation energy. All right. This is an exothermic energy diagram. Here's our delta H. Our delta H is negative here because this is the energy to go from reactants to products, and it's lower for products, so it's released. Activation energy is to get up the hill. Okay? Make sure you can sketch these kind of diagrams. Now, faster, slow, and energy diagrams. Well, here's reactants, here's products. We can't tell just by looking at these whether it's fast or slow. What if this is exothermic, right? What if it's endothermic? We can't tell just by these whether it's fast or slow. What happens to tell us whether it's fast or slow? We got to look at the hill. Okay? So, this hill is pretty high. So that means it's going to take a lot of energy to get over the hill. Wow, I'm popular. We're getting a lot of phone calls today. This energy is to get over the hill. Okay? So, fast or slow does not depend on where you start or finish. It depends on the hill. It's the climb. Okay, what a catalyst does is lowers the hill of the activation energy. So now this is a lower hill, so this is a faster reaction because it's got a catalyst. Okay, so all reactions break and make bonds. Okay, bond breaking absorbs energy, and bond forming releases energy. So one way to remember that is to barf. Ooh, did she say barf? I sure did say barf. Okay, breaking absorbs energy, forming releases energy, releasing during forming. Okay, so there's your barf. All right, but what does that mean? Well, here's an energy diagram. First, you got to break bonds. It's going uphill. Breaking bonds absorbs energy. All right, release energy when bonds form is the ARF. Barf, barf. Bonds absorb energy to break. They release energy to form. Okay, now if forming bonds releases more energy, if forming bonds releases more energy than it took to break them, then the downhill is bigger than the uphill, and that's exothermic. All right, but if bond absorption takes more energy than is released, then it's endothermic. So if the absorbing is bigger than forming, it's endothermic. But if forming is bigger than absorbing, it's exothermic. Okay, energy diagram in terms of bonds. So we could have two. We always got to go uphill first. That's the Ba. Breaking bonds absorbs energy. And this is the releasing energy when new bonds form. This is exothermic because the release is more than the absorb. Okay. All right, here the absorb is more than the release. So that's going to be endothermic. But you always got to go uphill then downhill. Uphill first. Okay. So finishing up here, exothermic reactions are favored in nature. Why? Well, let's look at what happens. This is low energy, right? This is lower than this. So nature wants to go low, right? Nature wants to go low with energy. Why? Think about it. If you're lower in energy, you're like chill, okay? I'm chill. I have low energy, I'm chill. Oh, this looks fun. Low energy, right? High energy is stress. Okay, that's high energy, that's stress. All right, so what does nature want? Nature wants low energy. The natural tendency of chemical reactions is to go lower in energy. Okay, there's something else we're going to talk about, and I'm going to introduce it here, disorder. Here's a word you're going to have to know later. It's the preview. Okay, disorder is favored in nature. Do buildings build themselves? No, nature doesn't want buildings. We have to work for it. Do things fall apart? Yes, so that's natural. Do papers write themselves? No, so that's not natural. And look at that. Wow. Okay, so to review, let's get going. Get a lot of phone calls today. But when you're measuring the rate of a reaction, you need change in molarity over time. Change of molarity over time. Okay, how much product or reactant is forming or going away? Over time. Time is opposite of rate. Okay, the higher the rate, the lower the time. The lower the rate, the higher the time. All right, home run derby is collision theory. Collide with enough energy at the right angle. Reactions occur in steps. That's the mechanism. The slowest step determines how fast. Complex shapes slow down reactions. Energy diagrams explain a lot, and so should you. All right, so read section 18.1. Do the graphs questions for these two figures, and you will get some bonus points, all right? And hopefully you get why I'm playing this song. Peace out, friends.